For structured, tabular data, deep neural networks consistently lose to decision trees. On traditional rows and columns, tree-based models deliver higher accuracy with less compute. Deep neural networks rely on continuous, normalized data spaces to calculate smooth gradients. Tabular data, however, is full of unscaled, non-homogeneous features, like mixing categorical zip codes with continuous salary numbers. This creates sharp, discrete boundaries that cause neural networks to struggle. To map these discrete boundaries, data scientists rely on the gradient boosting machine, or GBM. A GBM is an ensemble learning method that builds multiple weak predictive models sequentially to create a single strong predictor. Instead of training a massive network all at once, a GBM trains shallow decision trees, one after another. Each new tree is trained specifically to predict the negative gradients, the residual errors, left behind by the previous trees in the sequence. By adding these targeted corrections together, standard gradient boosting machines build highly accurate models, yet they are limited by rudimentary protections against overfitting and an architecture that ignores system-level hardware capabilities. XGBoost, or extreme gradient boosting, eliminated these bottlenecks. It re-engineered the gradient boosting framework into a unified mathematical and system-level architecture. The first pillar of its dominance is mathematical. XGBoost utilizes second-order calculus to optimize the learning function itself, rather than simply updating model weights. The second pillar is physical. XGBoost applies hardware-aware engineering, aligning its mathematical operations directly with CPU parallelization and memory chunking limits. To understand this framework, we need to deconstruct the specific mathematical operations that allow it to dominate modern predictive modeling. XGBoost achieves its results by perfectly balancing aggressive residual error correction with structural regularization that forces the model to remain simple. At any given iteration, represented by the variable k, XGBoost seeks to minimize a specific two-part objective function to determine its next optimal split. This equation represents the regularized objective function, which calculates the total score the algorithm is attempting to minimize. The first term is the training loss. It measures the model's predictive fit by calculating the difference between the actual data and the current predictions. The second term is omega. This is the explicit mathematical penalty applied to tree complexity. Inside that omega term are two critical variables: gamma, which penalizes the addition of any new leaves, and lambda, which applies L2 regularization to the leaf weights. L2 regularization is a technique that adds a penalty equal to the square of the magnitude of coefficients, forcing the model to keep those weights small and stable. Hard-coding these complexity limits directly into the objective function prevents the model from growing deep enough to memorize the training data. This guarantees the model will generalize accurately to new, unseen inputs. Optimizing general nonlinear loss functions, like log loss, directly for a discrete tree structure is computationally difficult. Log loss is a metric that evaluates the accuracy of a classification model by penalizing false classifications based on the probability of the prediction. To bypass this computational wall, XGBoost uses a mathematical workaround known as the second-order Taylor expansion. This visual shows a standard first-order gradient descent. Notice how it takes a blind step based entirely on the immediate slope of the straight tangent line, often overshooting the minimum. The Taylor expansion solves this. It wraps a parabola around the current prediction point to map the actual curvature of the surrounding loss landscape. To build this parabola, it uses the first derivative of the loss function, known as the gradient. This dictates the required direction of the mathematical update. It then calculates the second derivative, known as the Hessian. The Hessian measures the confidence, or curvature, of that update space. By combining the gradient and the Hessian, XGBoost approximates a complex loss function into a simple quadratic equation. Since the bottom of a parabola is easy to calculate, this simplifies the minimization problem. That calculus translates directly into an applied algorithm. By utilizing Hessians, XGBoost takes highly precise, confidence-weighted optimization steps. This addresses the overshooting errors that occur in older first-order gradient boosting machines. To physicalize this math into tree architecture, XGBoost calculates a structure score for any proposed leaf simply by summing its gradients and Hessians. This is the split gain equation. It evaluates whether a node contains enough error reduction to justify physically branching into left and right leaves. In the numerator, squaring the sum of the gradients ensures the algorithm aggressively targets and corrects the largest residual errors. In the denominator, dividing by the Hessian reduces the overall score if the curvature is high. This enforces conservative updates when the model gets close to the loss minimum. Finally, the subtractive gamma term acts as the explicit complexity threshold. The new split's gain must mathematically overcome this specific penalty to be approved. This serves as a built-in pruning mechanism. If the calculated gain evaluates to less than 0, the split is immediately rejected and the branch stops growing. The split gain formula is the bridge. It converts abstract second-order calculus directly into the physical algorithmic branching of a decision tree. On massive enterprise-scale datasets, checking every possible split point, a process known as the exact greedy algorithm, creates a severe computational bottleneck. XGBoost solves this with a histogram-based approximate algorithm. It groups continuous features into discrete buckets, accelerating how fast it can evaluate potential splits. It also introduces sparsity awareness, replacing the need for naive data imputation when dealing with missing values. This diagram illustrates a decision tree node evaluating a missing data point. XGBoost dynamically learns the optimal default direction for missing values during training by testing both paths through the split gain formula and choosing the route that minimizes loss. To process these calculations at scale, XGBoost utilizes in-memory column block structures. This allows it to evaluate these histograms in parallel across multiple CPU threads. XGBoost achieves extreme speed because its mathematical theory was rewritten to exploit the cache architecture of modern processors. The dominance of XGBoost catalyzed the development of specialized competitors, dividing the machine learning ecosystem into distinct architectural camps: XGBoost, LightGBM, and CatBoost. This split-screen visual compares the baseline tree growth architectures of these three leading frameworks. LightGBM relies on an aggressive leaf-wise growth strategy. It is optimized for speed and memory efficiency, prioritizing the nodes with the highest loss reduction, making it ideal for datasets exceeding tens of millions of rows. CatBoost utilizes symmetric trees and ordered target statistics. This allows it to natively process high cardinality categorical features, like thousands of unique text labels, without causing data leakage. These specialized models have industrial origins. CatBoost was engineered specifically by Yandex to handle the massive, heavily categorical demands of their search recommendation systems. Despite these alternatives, XGBM remains the industry baseline. Its stable, level-wise growth and rigorous mathematical regularization make it exceptionally reliable across diverse datasets. High-performance tabular modeling relies on an understanding of how specific mathematical choices, like second-order optimization and tree growth strategies, dictate model behavior in a production environment.